A very warm welcome to the 2021 edition of the Quantum Future Award, which is partly connected to the Quantum Future Academy as well, which happens to be parallel to that award ceremony. So this award has a reputation for being two things: tough and fun. And as last year, we are as live as it gets. In this particular case, that means live stream. But that does not take away that all the contenders, all the contributions did their best, because the work for an award has to be done before, not during the award ceremony. My name is Katja Schleicher. I'm an internationally working communication coach and trainer with a big heart for science and science communication. And that's why I'm very happy to be able to moderate this award and to guide you through the next 90 minutes, where we will see and hear and listen to 10 wonderful, thrilling contributions, all having to do with quantum technology. Because if the pandemic has taught us one thing, science needs to explain more easily what it's all about, what they mean. And in this award, and with me, I'm very happy when we can strengthen that voice. So a true driver of many quantum technology initiatives in Germany and in Europe is the German Ministry for Education and Research, the BMBF. With me here in the studio, and I'm very happy about that, is Professor Dr. Ina Schiffer, who is heading within this ministry the Department of Research for Digitization and Innovation. A warm welcome. She's a physicist herself, specialized in critical infrastructures and security of IT systems. One of the topics that has become more and more important, and where I think quantum technology can play an important role in that. Most importantly, within the ministry, she is driving quantum technology projects, which is, technology-wise, one of the most important things that could happen in the next couple of years. And that's why the ministry wants to be at the forefront of that development. So we come back to her later. In a while, I will introduce the other members of the jury to you. Every year since 2018, young scientists, engineers can apply for that award, either with their master's thesis or with their PhD thesis. This prize is awarded for excellence in quantum technology in many different departments and many different topics. And it's sponsored and it's chaired by the German Ministry for Education and Research. So since June, a jury with scientists and entrepreneurs has looked through all the different applications. And we are happy that the 10 best of them are here to present the results of their work. So the award comes with a nice prize. The winners are taking away prize money of 6,000 euro to be worked in a study or study travel or even in lab equipment. That is up to you, but not in cash. And the two winners of the second prize are awarded 4,000 euro. So before I hand over to Ina Schiffer as chairwoman of the prize, let me introduce the other two members of the jury today. Professor Oliver Benson is from the renowned Hubbard University in Berlin. A warm welcome from my side. He is a professor for experimental physics, and in our talk before that, he said, we always need time to set up a couple of our experiments, which now, when we do it online, is a little shortened. His special interest is in talent development of young scientists. Furthermore, he is involved in the strategy process of the Ministry of Education and Research. Professor Benson, what did surprise you most in all the applications you've been looking through?
Well, it's still remarkable what the progress is and how fast it moves forward. So in particular, looking back the last 10 years, but maybe also looking back the last 3 years, huge progress has been made. I'm looking more on the experimental side, being an experimentalist, but this is most impressive and still impressive to me. I hadn't thought that this would be possible maybe 10 years ago.
Yeah, time flies, right? In the quantum world, it seems like that 1 year is like 10 years, right? Thank you for that. From the industry side, we invited Dr. Alexander Regnert, who is a startupper. He founded companies, and of course, he is a physicist himself. He has founded a company that specializes in cryotechnology. So, as we know, data storage need energy and warmth, and mostly they are heated. So you are taking care for the good cooling, am I right? And as an entrepreneur, you've been involved in the selection of this award. What did you find most appealing so far?
I found most appealing that we have a really broad range of applications. So we're talking about applied quantum technologies, and it's really amazing to see both experimentalists and theoretical work in the field of applied quantum technologies, where we can see that this has become very hands-on nowadays. So that's really great to see, and I very much look forward to the presentation of the candidates.
The jury is involved in a pre-selection since June, and the pitches today can all of this give an additional boost. So the awareness for the next big thing, quantum technology, now that is something you altogether already created with your application, even if you do not win the prize in the end. Most importantly, from the political side, this award has a strong sponsor and content supporter. That's the German Ministry of Research and Education. And Professor Ina Schiffer is one of the chairwomen since last year, although the prize is already a couple of years older, and is one of the parents of that prize. And that's why she has the first word of welcome. Ina Schiffer.
Thanks a lot. I want to make one correction. Although I know most of the people here are physicists, I'm computer scientist and engineer, and I hope to see more of those also in the field of quantum computing. But maybe we can come to that later on. So, dear participants, dear quantum enthusiasts, dear colleagues, dear esteemed finalists, you are already a winner. Please take that with you of this Quantum Future Award. Thank you for joining us. It's really great pleasure to be here on behalf of the Federal Ministry of Education and Research, and I also can give you the best greetings from the Minister, Ms. Karliczek. So as we all know, quantum technologies promise to deliver disruptive change in areas such as data security, communication, sensing, and computing. It's exciting because ultimately we want to use this disruptive potential to benefit our societies and to improve the way we live and work. Quantum technologies will help us in this task by accelerating innovation and solving problems that seem to be unsolvable as of today. So I know that achieving societal impact may be well ahead in the future. However, we need to consider this already now. It's important to keep this goal in mind by all of us. So what is in addition very exciting is to see so many young people entering the field, being engaged in quantum technologies. We need you. We need you to build really strong research, strong innovation based on quantum technologies, to bring all together and to create a good ecosystem, a strong ecosystem on quantum technologies in Germany and Europe. We want to aspire to become one of the best ecosystems really in the world because it's so important. And to create good conditions for such an ecosystem, we try to find good measures and launched several measures already, because one of the good thing in all the crisis was that it brought additional push for quantum technologies. We received additional research funds to support initiatives, projects on the scientific and on the industrial side, and to support education and outreach, because quantum technologies are not that easy to comprehend. So let me give you two small examples. One is a big one. It's this financial support, which is up to 1.1 billion euros in the upcoming years on quantum technologies. We try to find good projects on hardware, on software, on both together, on processor side, on cooling equipment, to come up at the end with high-performance quantum computer, which is made in Europe, basically, which is designed in Europe, and hopefully also for which many components come from Europe. And for that, we need collaboration between academia and industry. It's really critical to be at the cutting edge and to have the transfer to the building of the quantum computer in mind. And secondly, as I said before, education and outreach is likewise important. And for that, we also try to focus on the promotion of young talents like you, to support networking and science communication. So beside this Quantum Future Award, we do have, for example, the Quantum Active Initiative, which supports projects that reach out to pupils, students, and the general public. The goal is to foster a better understanding of quantum technologies in all fields. So getting back to the strong ecosystem, so what does it need in addition? It needs not only you, but it also needs international ties and collaboration to spread across the international field with all the partners that are in this field active. So I'm, in that respect, also particularly pleased to welcome all the participants of the European Quantum Future Academy 2021 into this audience. That helps to bring together the researchers from different countries and to, well, work together, not only now, but also in the future. So we very much hope that from this event, you will take quite some insights and you will take it further and push the boundaries on quantum technologies even more. So about speaking how to push, or when speaking how to push boundaries, that is exactly what you did already. All of you created excellent master and PhD thesis. There had been many more applicants for this award. You are the finalists. As I said before, you are already winner by itself, by that pure fact that you are here with your presentation. We honor for the fourth time, as said before, master and PhD thesis, and the 10 of you presented the most outstanding thesis to the jury. So your thesis are on specialist algorithms for noisy intermediate scale quantum computers, or on gate optimization for gate-based quantum computing, or about electronics for scalable quantum processors. And I cannot present all, but you were going to do that anyway. So it was very impressive to see the quality of your thesis, and we are really looking forward listening to your award pitches. We are sure that both together is important when doing research. So you need excellent results, but you also need to be able to explain what you do, why you do it, what you achieved in your work, and that needs to be done over and over again. You will see it later on in your professional career. So, but as we've seen in the years before, many excellent presentations, this year also we will select an audience award, which is, so to say, chosen by all the participants in this award session. And when the jury, so to say, has the last discussion on the winners, I want all participants to vote online for the best pitches you see today. So this is, so to say, a next chance for all the presenters today to see if you make the best pitch for the presentations. Last but not least, I want to give special thanks to the jury members. We have here Professor Oliver Benson and Dr. Alexander Regnat, as presented before. I also want to thank Professor Christian Groß. You all supported us very actively in the evaluation process and in the, so to say, pre-assessment. Well, I talked already too long, so we are all very excited to have you here. Thank you for your work, thank you for your application, and we really look forward to your presentations. We say good luck, and we ask you to continue in research, to continue also to work interdisciplinary, and to consider here or there also to do the next entrepreneurial step, because that's important for the transfer, as I said before. We all need together to find the next breakthroughs, and maybe it's one of your results. So thank you for your dedication, for your commitment, for your engagement, for your upcoming research work as well. And good luck. Thanks.
Thanks for your encouraging words, Ina Schiffer-Decker. And the audience award, it does make it even more exciting, doesn't it? Because it gives it a different perspective. Am I right here? So? Right? So, dear interactive audience, sharpen your pens. It is up to you to decide about who is getting that award, right? It's not always an exclusive science communication training afterwards, but we come to the prize later on. After having heard the 5 master and the 5 PhD thesis, there will be a break for the jury to decide on the winners on the scientific side. So, and that is exactly the moment where you will see a screen in the link, a link in the screen window. That's the way it goes, right? You will have access to that link, get a code, and then you can vote. Just you, your voice, for the best presenter in your personal perspective, right? 15 minutes break, that will give you enough time to decide. What you have to do before is to pick pen and paper, truly analog, and take some notes. Because you have to remember afterwards who said what, and after 10, whom did you like most. So do not forget, when you listen to the pitches, that in the end, you'll be asked to vote. Ready? Then let's get started. For the first category, the masters, we had, Ina Schiffer-Decker already mentioned that, we had additional support from Professor Christian Groß, Professor for Experimental Quantum Physics from the University in Tübingen, and he is member of the Max Planck Institute in for Quantum Optics in Garching as well. He can't be here today, but he already gave his vote in the pre-selections. Thank you again for your support. All set? Let's get started. Our first finalist in the Masters category is Ricardo Chipoletti. He mastered in physics 3 years ago in Ulm, and he developed and optimized micro-sized mirrors that enable a better information flow between qubits and photons. Ricardo, good luck. Get right into it. 3 minutes to run.
Thank you very much for your kind introduction, and thank you very much for having me here today. So I'm going to start with a little love story. The love story of Romeo and Juliet. So quickly recap, Romeo and Juliet are in love with quantum technology. But their parents actually don't share that love, so they need to hide their communication from their parents. So they came up with a quantum network based on single photons. So the thing about single photons is that they are very small. And if we think, how can we look at something that is very small? It's just not our eye looking at something. Our eye is just collecting information. So we have always coming light from a source like the sun or a lamp interacting with our system and being collected by our eye. So if we assume that the smallest thing that we have would be cars, to see whether there is information going from Romeo to Juliet, the parents would need to throw another car onto those cars. And I think all of you agree that Juliet would actually notice if there was a car accident. So one possible source of single photons is a hybrid quantum system. In this case, by two mirrors, flat and a curved one, coupled to an emitter, for example, a nanodiamond. Such systems are very suitable for quantum engineering as they are very small, some micrometers in size, and have a high tunability. In my thesis, I focused on these curved mirrors. As you can easily understand, they need to be with a very smooth surface, as you don't want to lose any photons. So we used the high power CO2 laser beam to ablate some material from a fused silica sample. Yes, I was working in one of these cool laser labs at Ulm University. So then we need to know actually how this structure became. So we used the Twyman Green interferometer to directly reconstruct the structure and have a look at it. Here you can see some exemplary phase map and the reconstructed profile. We have seen that especially a multi-shot technique using 2 or 3 shots of the CO2 laser have produced very good results. Thank you very much for your attention and have fun today.
We will, Ricardo. Thank you very much, because it's very, for me, I studied literature, and of course you had me at Romeo and Juliet, and to turn quantum technology into a love story. That cannot go wrong. Thank you very much. Thank you. So from pasta, we go to paella. Esther Cruz Rico is a mathematician and a physicist. Women do always double things. She studied in Madrid and in Munich. And due to her research, it became possible to certify coincidental numbers that bring quantum computing closer to commercial use, which is indeed something we are all waiting for. Esther, on your marks, ready, set, pitch.
Thank you. So we have now the first operating quantum computers, and they are reaching a limit in which we cannot simulate them anymore. While this opens the door to a new range of computation possibilities, it also raises the following question. How can we check that the quantum device is performing the right operations if we cannot make predictions beforehand? Of course, there are problems that are very easy to verify, like factoring. Just multiply the two factors and check that you get the original number. But now imagine that I send the quantum computer, that I draw here as a black box, some instructions to prepare some quantum many-body state. And I ask to measure afterwards. I will get some zeros and ones as an output, and it's not clear now how to check that this output indeed comes from the state distribution. Note that as users, we cannot just open the black box, because we usually only access the quantum device through the cloud. In this case, we see that the quantum computer is not trusted and might even try to cheat me. So this could be a serious problem, because for many tasks, we need to be sure that the quantum device is performing right. For example, imagine that I want to send an encrypted message. Most cryptography protocols need random numbers, which are very easy to generate with a quantum computer, because the process of measuring quantum mechanics is intrinsically random. But what if the quantum computer is fooling me and sending me some predetermined number? Well, then it could just decrypt my message and we certainly do not want that. So to solve this problem, people have already proposed verification protocols, but they either target fault-tolerant devices or require the full simulation of the quantum circuit, which will be unfeasible in the near future. So in this thesis, to overcome these limitations, we provide a first step towards an efficient verification protocol for current devices. We propose a family of quantum states that we can prepare and verify. The preparation is done adiabatically, which means that we smoothly and slowly change the parameters of our quantum circuit to interpolate between an initial state that is to prepare and the target one. For the verification, we propose a two-player game between a classical verifier and a quantum computer. The verifier poses challenges to the quantum device by using some statistical properties of our quantum state. If the quantum computer answers consistently, then we can convince ourselves that indeed it has prepared the right states. We also discussed that if the quantum computer tries to cheat me, well, it would be easy to detect. So to summarize, in this thesis, we have two results. The first one is about how to prepare a large family of quantum states, and the second about how to verify them. This would allow the verification of untrusted or cloud-based quantum computers in the current noisy regime. As mentioned in the beginning, it also has practical applications, by generating certifiable randomness, which must be the first commercial application of quantum computers. Thank you.
Skill, or the most important skills, besides next to being smart, that young people that want to do that need to bring to quantum technology? What does it take?
Well, maybe one has to be somehow looking in two directions. So on one hand, you have to be focused on your own research, of course. Mm-hmm. But since quantum computing is still a very interdisciplinary field, you have to be open also to other areas which may be far away from you. So you have to deal maybe with some electronics, but you also have to know about the algorithms, or you have to develop quantum states, but you also have to know the boundary conditions in a lab. And that's quite challenging, and I'm very much impressed how our candidates were able to master these tasks.
Yeah. Thank you very much. And indeed, the interdisciplinary aspect seems to be gain more and more awareness and attention in the quantum technology arena. And let's follow Johannes Jakob Meyer now to Copenhagen. Johannes, are you in Copenhagen? Is that right?
No, I'm actually pretty close.
You're back in Germany, okay. But this is one of the beautiful things in times where we meet each other very much online. It's very hard to tell where people are, right?
Yes.
So you were doing research on developing algorithms that will many problems, will solve many problems that are not tackled at the moment. You were studying in Berlin. Yes, you are now in Berlin, indeed. Johannes, developing algorithm is the next big thing. So the algorithm stage is all yours.
Yeah, thank you for the introduction. So quantum technologies, especially quantum computers, will end global warming and world hunger. Yeah, headlines like this, they come directly from the quantum hype machine. And I think we all agree that this is a little bit too much. But I really do believe that we can use quantum technologies to push the limits of what is possible. And it is our duty as researchers and industry partners to make it happen. And one technology that I believe can soon outperform classical techniques are quantum sensors. A quantum sensor it exploits quantum effects to improve the precision of measurements and therefore allows us to get better microscopes or MRIs. But the performance of quantum sensors is still limited. One factor is noise, as with any near-term quantum technology. Another one is that the underlying hardware platform usually has limited capabilities. It's therefore crucial to optimally design sensors to cope with these limitations. But designing quantum sensors is becoming pretty hard pretty quickly if done on a classical computer. And therefore, in my thesis, we propose a different approach, namely to use quantum technologies themselves to design quantum sensors, and in that way to perform quantum-aided design of quantum technology. And to do so, we take inspiration from near-term quantum computing and use a hybrid approach. And there, a classical controller is combined with a quantum device that models the quantum sensor. And in an iterative feedback loop, we are updating the design parameters of the quantum sensor until we are satisfied with its performance. But to get this satisfaction, we need to measure the performance. And in my thesis, we advocate to use a quantifier that incorporates all aspects of the sensing scheme, including measurements and post-processing. And this really gives us the maximal flexibility. And this maximal flexibility allows us to have a very wide range of applications. So we can use it on different hardware platforms, from optical systems to spin systems. And we can even use it to optimize sensors as they are sitting in the lab. And it doesn't even stop there. We can also make use of a near-term quantum computer to model the quantum sensor and use that as a surrogate in the design process. So in the end, we do not only have a way of really get the most out of quantum sensors, but also promising application of near-term quantum computers. And almost 3 minutes ago, I told you that we, as researchers and industry partners, we need to make quantum technologies happen. And I believe that the idea of quantum-aided design of quantum technologies is a way to do so and to really get the most out of those technologies that are slated to transform our future. Thank you.
Thank you very much. It's always good to hear when a young scientist is able to present his or her ideas in a way that are absolutely compelling to the rest of the world. Thank you for that. Ina Schiffer, our next contender, has two completely different studies. He's a philosopher and a physicist. And there is a lot of physicists who have been done that earlier. But do you see that we are going to see in natural science more of these combinations, people who do physics or technology and then choose a completely different subject on top? Is that something you you are in favor of, or do you see more of these developments?
Well, definitely I like to welcome such approaches, because I think evidence shows that many new unexpected insights are exactly at the interfaces between fields or disciplines. Of course, you can always also optimize within one field and find very new results, but I think there are very impressive results at the intersections of different fields. So it's most welcomed.
Yeah, and indeed, surprise is luring behind every corner. And that's why we are absolutely excited to have Benjamin Schiffer here, who is indeed a physicist and a philosopher. And he studied at the LMU in Munich, and his thesis combines the strengths of different algorithms in his master thesis. So he not just used one algorithm, but combined the strengths of all of them. Benjamin, 3 minutes on stage are yours now.
Thank you. So the first quantum computers are now available. And in my master thesis, I present one novel idea, how to use noisy intermediate scale quantum devices, NISQ, that is the early quantum devices, for the preparation of ground states. Why ground states? Ground states give the configuration of a system with the lowest energy. And these are really important for two scenarios. One, for quantum systems, they give all the properties that are required for applications such as new high temperature superconductors or new molecules for chemical processes. But they're also relevant for classical problems, for classical optimization problems, as they encode the solution to them. You might know about the famous traveling salesman problem. These problems arise in industry every single day. Now, one powerful algorithm to prepare these ground states is the Adiabatic algorithm. The Adiabatic algorithm, as you already heard before, starts in the ground state of an easy problem, a toy problem in the beginning, which is slowly transformed up to the target. The target then has the ground state that we want to prepare, which is very difficult to find. Let's make this picture more detailed. We want to stay all the time in the ground state following these blue arrows. However, we have to be careful. We have to do this very slowly. If there's a difficulty along this path where the ground state becomes very close to the first excited state. Now, the computation time of early quantum computers is limited. So it's crucial to be efficient, where to be slow and where to be fast. However, Unfortunately, we do not know in advance where to be slow. And this is a problem I'm tackling in my master thesis. I'm proposing a variational quantum adiabatic algorithm. We split the adiabatic path in parts, and now in a variational scheme, by repeating many speed combinations, we find the profile that optimizes where to be fast and where to be slow. This way, the computational time is used in the most efficient way. This algorithm, as said in the introduction, thus combines the best from adiabatic quantum algorithms and variational quantum algorithms, such as the famous QAUA. In my thesis, I benchmarked the algorithm using state-of-the-art numerical methods, that's tensor network techniques, on high-performance supercomputers that can in some cases compete with the best quantum computers. The simulations show that for a system that has the same number of qubits as the current Google Sycamore chip, we can reduce the runtime of this adiabatic algorithm by a factor of more than 10. Our algorithm really identifies where we have to be slow and where we can go faster, thus using the computational time as efficiently as possible. Importantly, we also give new quantum methods to reduce the number of repetitions learning this adiabatic speed profile. I am deeply convinced that this variational quantum adiabatic algorithm and the work that will build up upon this is highly relevant for making early quantum computers useful. We're talking to colleagues at Harvard University to run this algorithm on real quantum hardware so that these ideas can also have a real world impact. Having a useful and efficient quantum algorithm for ground state preparation would be a game changer for the automotive industry or for the development of sustainable chemicals, new pharmaceuticals, and so on. I hope you're excited as I am, and I thank you for your attention.
Thank you very much. Alexander Regnert, when you hear that and you hear the excitement of a young scientist, is in your mind as someone coming from the industry side, is there already, when you hear that, a plan in your mind to say, oh yeah, this is what we could do with this? Is there already an idea forming, or how do you deal with that when you listen to things like that and know how you could put them into practice?
Perhaps not directly related to what we're doing, because we're really doing very hands-on work, screwing together machines. So that's certainly something which I wouldn't optimize using a quantum computer. But I think Benjamin has perfectly shown and pitched to us how important the preparation of these ground states is. It's a general issue, and we need a good solution how to prepare these. And it's a huge class of problems that can be solved, reaching from chemistry to pharmacy and also to machining, actually. Perhaps not in our company, but for many other manufacturers, that will be a game-changing rule that quantum computers can play if they can make use of these algorithms. Yes.
Thank you. The last contender in that category is Cem Gunotorn, and in his master thesis he dealt that the efficient fiber coupling from color centers in diamond structures. And his research helps to make quantum devices more scalable. Cem, are you ready?
Of course.
Let's do that. 3 minutes are yours.
Okay. Those of you old enough will remember sitting in front of your computer in the late 90s and connecting to the dial-up internet, waiting and waiting to slowly download your email with a 56 kilobit per second speed. 20 years later, internet connections are 10,000 times faster thanks to the fiber optic infrastructure. In the future, the classical internet will be superseded by the quantum internet, as it will provide complete security based on quantum entanglement and do things we can't even imagine today. Presently, the largest state-of-the-art quantum network is a 3-node quantum network built by the best scientists in Delft. This network can create an entanglement link, a connection, only every 90 seconds, which is even behind the classical modems of the 90s. One of the main reasons for this low speed and a 3-node limitation is that the light particles, also called photons, that carry the entanglement are very hard to catch. Let me explain you why by using an ordinary light bulb in your kitchen. A light bulb emits light everywhere, but you want to direct the light to illuminate, let's say, your kitchen table. What we need in the lab is practically the same, only our quantum light bulb is 1 million times smaller, is made out of diamond, and the light it emits from its color center contains quantum information. Moreover, there are 2 other challenges with the diamond. One, it's a trillion times less bright. And two, most of the lights get trapped in it due to internal reflections. So how do we get around this? In your kitchen, you use a lampshade to direct the light. In my thesis, I transferred the concept of the lampshade to diamond that have sizes of only several hundred nanometers, 1,000 times thinner than our hair. I invented a promising new nanostructure called the inverted nanocone, which was the core invention of my thesis. Still, directing the light into one direction is not enough. We must couple it to optical fibers to connect devices within a quantum network. But surprisingly, before my thesis, fiber coupling from these nanostructures had not yet been optimized. To enable efficient fiber coupling, I adapted and developed software tools that simulate how much of the photons will be caught in this fiber and optimized inverted nanocones. With my method, I can easily extract the best values for the dimensions like the height or radius and provide my colleagues in the clean room at the Ferdinand Braun Institute a recipe to fabricate such structures. In the end, we published a manuscript where we reported that a 20 times improvement compared to bulk is theoretically possible with an ideal inverted nanocone. At the second part of my thesis, I developed an experimental setup where I could analyze these nanostructures in real life. Now, in my PhD, I'm continuing the same work to achieve higher entanglement rates with the hope of increasing the size of the networks and bringing the high-speed quantum internet closer to reality. Thank you.
Thank you very much, Cem, and all the other pitch presenters from the master thesis category. Professor Benson, up to now we heard quite a high quality in terms of presentation content, communication. So if you look at the future generation of quantum scientists, what skills do you have to bring to make it in that category? What is important? What do you see?
Yeah, we saw very impressive presentations already, and maybe that's a trick. Quantum physics is a little bit hard to explain. That's the very nature of it, that you cannot easily grab it. And so we've seen, I think, very nice examples how to give some analogies, but at the same time be careful enough not to oversimplify things. And that's required. And so we saw 5 very nice examples of that.
So complex enough and at the same time easy to understand. That's where the trick is, where the trick lies.
Yes, the right balance. So I think
right
not making things too simple, because nature is not always simple.
Yeah, no, indeed. And I hope it is not, and these presentations have not been easy for you, audience, because this is already, has been the first part. And if you think of the audience award, you have to decide about, this is probably already worth taking some notes. And while you do that, we dive into the PhD category, right? Let's hope that Annabelle Board has all the qualities Oliver Benson has been talking about, taking it easy enough, explaining things easy enough, but showing the complexity, on the other hand, of all her subject. She joins from Munich, Annabelle, and since this year, she is a postdoctoral ITMP fellow at the Center of Astrophysics from Harvard. And already that is an achievement. So being here means you have even more ambition to win that prize as well. All right, then that's the spirit. That's what we want to see. Annabelle talks about the effects of high-temperature supercomputers. Superconductors, you see? Superconductors. That's important. Annabelle, do it better than me. 3 minutes are yours.
Yeah, hi, I'm Annabelle, and I'm very excited to be here and tell you in the next 2 minutes and 50 seconds a bit about my thesis on probing strongly correlated many-body systems with quantum simulation. And let me tell you why this is so exciting. So 35 years ago, these two gentlemen discovered high-temperature superconductivity in the cuprate materials. And what this means is that they found a material which conducts without resistivity at much higher temperatures than previously thought possible. And this has, of course, a lot of important applications, for example, in generators or lossless power transmission. The problem is now that we don't really, until today, know why these materials do it. So there are a couple of things that people agree on. One is that the charge carriers have to move around in pairs through the system. The other thing is that these materials look something like this, and the interesting physics happens in these 2D copper oxide layers. And most people agree on that we can describe this with the two-dimensional Fermi-Hubbard model. So this is now a quantum many-body system. You have fermions with two spins up and down, or depicted here in red and blue. They want to lower their kinetic energy by hopping around the lattice, but they have to pay a penalty U if they sit on top of each other. And if we are now at half filling, so if exactly one of these particles per lattice side, we fairly well understand what happens. So at high temperatures, we just get a metal. And as we lower the temperature, we first get charge orders. So one particle sitting in each lattice side actually. And as we lower the temperature even further, we get spin orders. So spin up wants to sit next to spin down and so on. And the problem is now in this phase diagram, we've been talking about this axis now, but the interesting stuff happens here at finite doping. And finite doping means that we go away from half filling and we put holes into our system so that our particles can hop along. And this is now very hard to actually figure out what happens in this model. And this is where I come in with my PhD. And so what I did is in a lot of detail understand what a single hole does. So if you have your quantum antiferromagnet, and this is just a cartoon picture here, and you put your hole into it, then it wants to move around with this to lower its kinetic energy. But as it hops around, it displaces the spins, and along its path, it creates a string like this. And so here along the string, the spins are now aligned instead of anti-aligned. So this costs us energy. The nice thing is now that we can reduce this to a single particle problem in the description. And this is something that we theorists love. So we can predict a lot of properties, and to compare those properties to some actual simulation of this model, we collaborate with our quantum simulation friends. So they take neutral atoms and optical lattices, and then they can take actual pictures of these atoms that realize directly this model. And so we can, for example, that's something that I spend a lot of time on, directly look for the patterns of these strings and find them in those pictures of these atoms. And based on the description of a single hole, we have now identified a mechanism how two of these charge carriers pair up together. And of course, we hope that this will lead to an understanding of high temperature superconductivity.
Thank you very much, Annabelle. Ina Schiffer-Decker, I have to ask a question. You probably heard the question 100,000 times. It may be the 101,000th. When are we going to see more women like Annabelle in this industry?
Fortunately, we see them already now. And I hope that we continue this way. The numbers show that, well, it's 50-50 with so to say, results in studies. And I hope that up the career, we also see those women in later stages. But above all, it's important, I think, that young people join, and those young people are 50-50, and that we learn to also tell young ladies, well, also the STEM disciplines or something that you could do.
Mm-hmm. Thank you. Our next contender is Pascal Serfontaine, and his PhD work is as impressive as Annabelle's because he researched how the quality of Gatta operations on gallium arsenide qubits could be enhanced. Pascal, could you please enlighten us about that subject? 3 minutes.
Yeah, sure, my pleasure. Sure, my pleasure. I happen to be an expert on gallium arsenide-based spin qubits. So first of all, let me say I'm really excited to be here and present our work. And let me start by saying that quantum computers, as Johannes pointed out previously, are projected to solve many important computational problems currently intractable with current supercomputers, like global warming. Perhaps on a more realistic side, one example of a potential quantum computer application is finding a chemical process for fertilizer production, which could reduce the world's energy consumption by up to 1%. However, for many interesting applications, millions of qubits are actually needed. And currently, the only technology able to produce billions of functional units at low cost is the semiconductor industry. In addition to sheer qubit numbers, each qubit also needs to be able to perform basic calculations, so-called logic gates, with an error rate of much less than 1%. To enable large qubit numbers with accurate gates, my colleagues and I researched advanced control techniques and applied them to semiconductor-based qubits. For the experimental part of our work, we first installed a state-of-the-art cryostat and cooled down gallium arsenide-based semiconductor chips we specifically designed for our experiments to about 100 millikelvins. We encoded in our system qubits using the spin of just 2 single electrons. This allowed us to completely control the qubits by manipulating gate voltages on a nanosecond timescale applied via these wires. Based on characterization measurements we performed, we created a sophisticated computer model of the qubit, including noise and non-linearities in the control. We then used this model together with numerical optimization to find voltage pulses creating the most accurate logic gates. In order to account for errors in our not so perfect qubit model, we then collected data characterizing remaining gate errors in the experiment. We used this data to further improve the computer-generated voltage pulses by a little bit, repeating this process, measuring errors, and correcting them over and over again in a feedback loop. We were able to reduce error rates for single qubits to about 0.5% for the first time actually in this material system. And let me say that working with these qubits, we realized firsthand that another hurdle for quantum computation is actually autocorrelated noise, for example, in the control voltages. You can see an example here in blue. This is an autocorrelated noise trace as opposed to a white noise trace here. And what these noise correlations do to an algorithm, which is composed of gates, which work well individually, is it can make it actually worse than you'd expect. And this is, of course, a threat for quantum computation, which generally considers gates as being completely independent and non-interacting building blocks. To quantify the effect of autocorrelated noise, we developed a formalism which can be used to describe algorithms in terms of the individual gates, plus the correction term shown in dark blue here. And these correction terms can then be analyzed to develop gates and algorithms which perform better in the presence of noise. The experimental and theoretical techniques we developed for both of these projects are quite generic and can be applied to other qubit types as well. For this reason, I think that our work has significant implications for operating and even designing quantum computing hardware, even beyond semiconductor spin qubits. Thanks very much for listening in.
Thank you very much. Andreas Regner, does it take us too long to bring ideas, as for instance, the one from Pascal, into the practice, into companies that really can turn them into services, products, solutions?
Well, I think it takes a long time, that's for sure, but on the other hand, it's a very complex problem. It's a complex machine we're trying to build. And I also think we're on a good way. It has to be a joint effort, and many people are now working on it. And I think that the work Pascal has just shown is very exciting and promising, as it just shows that one of the most promising candidates, semiconductor-based here, even gallium arsenide-based qubits, could be used for these processor technologies. And we have a working industry in that area. So I think it's very exciting. And we should make use of his work and the work of others to push this forward. Yeah.
That is good to hear, that there is a resonance in the industry, that the companies wait for these things to be put into practice. And Lotte Geck, our next contender, dealt in her PhD with something very practical as well, in terms of still a theoretical exercise. She wanted the necessary electronics to steer the qubits to be brought as close as possible to them. And the results sound very promising, don't they, Lotte? Good luck with your pitch.
They do indeed. Yes, and now I can also share my screen. Thanks. So, very nice to be here and see everyone. And one very prominent and well-known application of quantum technologies is the quantum computer. Because the quantum computing is very interesting, because theory predicts that tremendous progress can be made in quite a few fundamental problems. Use cases for these problems are, for example, drug development, material research, but also all kinds of optimization problems. And as already said before, in order to fulfill this promise, the quantum computer needs millions or even tens of millions of qubits.
which are the quantum processing units, and can, for example, look like this. Now, while quite a few people do the important work of figuring out how to best build qubits and also how to best operate them, the focus of my work was more on how to get from the current few qubit experiments to an actually compact computer. And in general, there has not been too much research on this so far, but if you want to build a quantum computer, it's very essential. Now, to operate even just a few qubits is quite challenging. Typically, a qubit needs a very sophisticated cooling machine, short, a fridge, and also quite complex signals to operate, and the associated electronics to go with it. And as you can see, this typical experimental setup is quite fitting for a few qubits, but it's not really a compact computer, nor is it usable for millions of qubits. Now, to make this more scalable, it is necessary to especially reduce the numbers of cables connected to the fridge, because cables conduct heat, and this can potentially disturb the qubit. One way to go about this is to use integrated circuits. And these integrated circuits are then tailored specifically to this function, and they also have the advantage that you can directly connect them to the qubit. In my work, I came up with a control system, an electronic control system for qubits, and I took a detailed look on how this could be used to control many qubits. The results are quite promising, but if you want to control a very large number of qubits, there's still further research necessary, also in the semiconductor technologies. Another hindrance to the scalability is also the heat produced by circuits inside the fridge. Then another part of the work of my thesis was to develop a hybrid model with qubits, but also with electronics. Because right now, the interface and also the specifications for the electronics are quite unclear. With this model, it is now possible to simulate how integrated circuits and the noise can affect qubits. And especially on this topic, there are quite a few points still open, which means that there's a lot of research still to be done in the future. Thanks.
Thank you very much, dear Lotte. And as you see, all this year's contenders have been already even more practical as the ones last year. And our next one is Patrick Winkle, and Patrick indeed tried something similar in his study, in his PhD thesis, which he did at Karlsruhe Institute of Technology. And he asked himself the question, what are strong quantum processors made of? And especially he had a look in the combination of superconductive qubits with granular aluminium. That seemed to be a very promising combination, wasn't it, Patrick? The virtual stage is all yours. Patrick, hörst du uns? Patrick, are you with us? I'm frozen on your screen. That doesn't need to be a bad thing in particular. I see you moving, so, and I don't hear you. Did you switch on your microphone?
I'm sorry. No.
Hello, there you are. That's all.
Yeah,
that's
sorry.
all good. No, don't.
I'm sorry.
Take it easy. Take it easy.
Okay.
Stage is all yours. Welcome to the show.
Thanks. Hello. My name is Patrick. I'm a scientist at the Karlsruhe Institute of Technology, and the focus of my dissertation was to develop superconducting quantum circuits for applications in quantum sensing and quantum computing. And in both of these fields of research, an important aspect is the implementation and the control of quantum bits. And therefore, on the left-hand side of my slide here, you see the conceptual visualization of a quantum bit. And for that, I'm using the block sphere, where the logical states of the bit are located at the poles of the sphere, 0 here and 1. And the state of the quantum bit is represented by this green arrow here in the center. And it can take any value on the surface of the sphere, meaning it can be prepared in any arbitrary superposition of two logical states. And while a single element is already pretty interesting for quantum sensing, for quantum computing, many of these elements are put together, interconnected in a quantum processor to create highly entangled state to solve some mathematical problems with hopefully real-life applications exponentially faster than their classical counterparts. And so one of the key challenges during this process is actually to extract information from the processor in the form of a flow, a series of classical digits, which are represented here by this series. And as you can see, every digit here is fuzzy because in a real-life experiment, there's actually noise. And surprisingly, the noise that we see is actually dominated by the measurement apparatus itself. So during my PhD, I developed together with my colleagues a quantum amplifier, and this quantum amplifier increased the signal to noise ratio by an order of magnitude. And this is visualized here by the absence of the fuzziness in the digits. And with this technology, we were able to measure continuously the time evolution of a superconducting quantum bit, which you can see here in the lower part of my slide. And we can do that in 500 nanoseconds, which we now reduced in a recent publication, even by a factor of 10. And having said that, at the moment, we're distributing this amplifier technology with our collaborators inside and outside of Europe. And because this has been a pioneering experiment in Germany, we're writing a patent to protect it for the German quantum industry. Yeah. And with that, I would like to thank you. And yeah, thanks.
Thank you very much. And as you can see in the virtual world, you always get a second chance to restart. This is actually like real life. Thank you for your contribution. For our next contender, our last one in the PhD category, as far as I know, we go to Boulder in Colorado. Is that right, Giorgio? You're still there?
Yes, I'm here.
Very early in the morning for you, am I right?
Yes, the sun is just coming up.
Oh, that is beautiful. So Giorgio deals in his PhD with quantum communication. In particular, the minimization of disturbances with ion qubit gate operations.
So,
go for
hello
it.
Everyone. In my research, I work toward the development of a scalable quantum computer based on trapped ions. Scalable means that the physics and technology behind our approach must be able to operate on a large number of quantum bits, not only the few actually used for research. The main achievement of my work was the design, demonstration, and operation of a self-contained universal quantum processing unit, where qubit operations are performed in a scalable way. In trapped ion quantum computing, it is common to implement quantum gates using laser systems. These are much bigger than the trap chip itself and typically very difficult to control. Instead, I implemented quantum gates using microwave circuits, which are integrated directly into the ion trap. Microwave technology is in a very advanced state thanks to consumer electronics. So microwave signals have the advantage they are much easier to control for high-fidelity quantum gates, which are integrated directly into the trap chip. To interact the ions in the desired way, the microwave field needs to have a very specific shape. So to obtain the optimal field shape, I had to perform an extensive amount of simulations. The ion chip trap I designed was then built using a now patented microfabrication process. The most challenging elementary operation for a quantum computer is the 2-qubit entangling gate. For scalability, using quantum error correction protocols are required gate errors of about 0.1% or better. In my first attempt using standard protocol, we obtained an error of about 2%, which was quite good, but not yet good enough. These 2% errors comes mostly from the joint motion of the two ions inside the trap. Even if our ions are cooled almost perfectly to the 0 point of motion, imperfections in the potential and the residual thermal motion can induce error in the quantum gates. Using quantum optics arguments and numerical simulations, I proposed an amplitude modulation protocol to fight this error. By engineering the signal in the appropriate way and when the signal in the appropriate way, that was connected to the ion motion have been almost eliminated. These allow us to implement a quantum gate with an error of 0.3%, already sufficient for some error correction protocols. The residual error is now mostly related to the internal state of the ions, where experimental protocols to further reduce it already exist. The results of my thesis have been the basis for an increase of activity around the processor registers which I devised. Scaling such processor is now pursued within the QVLS initiative and by a new BMBF project. My design will be complemented by other registers to provide a universal and scalable quantum computer for challenging quantum algorithms. Thank you for your attention.
Giorgio Sarontanello, grazie. Thank you very much for with us being up so early in the United States. So now there is two things happening. First of all, the jury is taking 15 minutes of conclave to come to a final decision about the awards for the master thesis and the PhD thesis. You, on the other side, the audience, you are invited, as I already said, to have a look at your notes and to follow the link that you are going to see on the screen to a Slido, our voting tool. There is a short code you get for that and a very short link. So please, the voting channel is open now for exactly 15 minutes. And within 15 minutes, you have the chance to vote for your audience award winner, the person where you say, wow, that was the best presentation ever. And all of us, we gather back here 5 minutes to 5. That is easy to remember for everybody to celebrate the winners and the second places and of course the audience award. So see you all back in 15 minutes and please go vote. Link for that in the screen. everybody. Nice that you stayed with us, that you voted. We've seen there were more votings than we ever expected. That's a very, very, very good sign for our new award, the Audience Award. But before we come to that, we have 2 second places and we have 2 winners of the Masters and the PhD category. Before Andreas Regnert is announcing the winner in the Masters category, Andreas, I want you to ask one more question as a founder, as somebody who is passionate about setting up companies and building on technology. How important is timing in the startup world in comparison to science?
First, a small correction, Alexander.
Alexander.
And then second, timing is crucial. Actually, it's very important. Yeah. Perhaps one of the most important things concerning entrepreneurship and founding companies. So I totally agree that it's a crucial issue, and to put this in the context of today's event, I think we're now concerning quantum technologies at a point where we're about where we can harvest what has been done in research many years ago. So timing here is also crucial, and it's great to see that here are so many young researchers who did a great job. Did fantastic work, and I'm very pleased to see that some are really working on algorithms and hardware which is close to real life, real world applications. So it's fantastic to see this.
Closest to window, Alexander Regnert. Forgive me for that, and please let us know who is the winner of the second place in the Masters category.
So it's my great pleasure to announce the second prize in the category Master Thesis of this year's Quantum Futur Award. It's a great pleasure also because the prize goes to a candidate from Munich. And I'd like to congratulate Benjamin Schiffer for his thesis, his master thesis, about variational quantum adiabatic algorithm for noisy intermediate scale quantum devices, NISQ devices. Benjamin, congratulations for your fantastic work and your great pitch.
Well, thanks, Alexander, for your very kind words. I'm very humbled. I was able to convince you of my thesis among these other great pitches. I really enjoyed the opportunity. I learned a lot from everybody else who took part, and so thanks to the jury, but also thanks to the other candidates for this really nice event and wonderful talks. Thanks.
Thank you, Benjamin. Sincere congratulations. And for the second place in the PhD category, of course, it's Professor Oliver Benson. But before you tell us who is awarded with second place in this category, what is, in your personal perspective, one of the most exciting projects you can think of in quantum technology at the moment?
Oh, that's hard to say, because if I mention now a specific technology platform, a great fraction of you will be annoyed about this. But we do see, and that's what I think is impressive at the moment, that real problems are being solved now, problems that are of relevance. And I think this will be definitely the major role of these devices and systems. But we do see the transition that, as said, problems of relevance are being solved.
Yeah, wonderful. Thank you. And now please announce who is the winner of the second place in the PhD category.
Yeah, it's my great pleasure to announce the second winner. And before I do this, I would like to congratulate all of the finalists. It was very hard, I think, to make a selection, as you can envision. However, we had to find one. And so this goes a little bit in my comments that I gave. So you can ask, if we have a quantum device, or the quantum device that we have today, can we give the device a real problem that's being solved? And in this category falls the second prize in the PhD category. It goes more in the direction of quantum simulation, and the prize, it's my pleasure to announce, goes to Annabel Bort from the Technische Universität, Technical University in Munich. And so we were also impressed about your enthusiasm for science that came out in the pitch, but also the thesis was very impressive, that you can do offer hardcore science problems to a simulator and get an answer. Congratulations.
Yeah, thanks so much.
Go ahead.
Thanks so much. This was really a really fun event, and I'm really grateful for the opportunity to be here today.
Thank you. Congratulations to you. Ina Schiffer, the ministry is putting a lot of energy and passion and effort into all these quantum technology projects. Let's move ahead 5 years from now. What would be your dream scenario for quantum technology in Germany and maybe even in Europe?
Well, thanks for that question. As we all know, there are different fields in quantum technologies. We have heard today about all of them. So sensing, communication, computing, also cryo technologies. So all the supplementary things that we need to make those quantum systems work, as well as the theory. So from theory, we are engineering to application. All of that is important. And I hope that we see more uptake of second-generation sensing in the industry. I hope to see first products on quantum communication, and I hope to get a clearer picture where to scale quantum bits for quantum computing of, so to say, more real application scenarios. Yeah. There are, so to say, I think maybe 5 years are not enough, but I'm sure in sensing and communication.
And it will give enough room to everybody who wants to apply for that award next year. But now, without much further ado, who are the 2 winners in the master category and in the PhD category? Wherever you want to start.
Well, thanks a lot. Thanks again to all of you for your great work, for your excellent results, for your very nice, interesting presentations. And it's hard to choose, as always, so it took us quite some time. So at the end, we have very clear winners, which also means, I want to repeat it, you are all winners, you are all seen by the community. A lot of people took part in the session today, and I think you will get some nice context from that. Anyway, there are to be winners, and we have 2 winners. I like to start with the Master Thesis winner. So it's my really great pleasure to announce this year's Quantum Future Award winner in the Master Thesis. This award stays in Berlin, and it goes to work on quantum circuits. And we have seen a brave presentation, which was different to the others. You started with an interesting announcement after my political statements, where we want to get in quantum technologies, good things. So the award goes to Johannes Jakob Meyer for his master thesis on applications of parameterized quantum circuits on near-term quantum devices. Congrats.
Yeah.
Congratulations.
Thank you so much. I'm also really humbled to receive that prize. And I mean, we've all seen this extremely huge quality of all the pitches and all the projects. And so it was a real pleasure also preparing this. Just thank you so much for giving me that opportunity to pitch here, and for that prize. I think everybody else would have equally deserved it. Thank you so much.
Well done. Sincere congratulations. And in the second category, who is the winner there?
Definitely. And here again, it's really my great pleasure to announce the year's Quantum Future Award winner in the category PhD Thesis. And this one doesn't stay in Berlin. It goes to another place. It goes to a well-known place, also in quantum technology. It goes to the, how is it, said in English. I even don't know, RWTH, that's not right. So
RWTH.
it goes to the Aachen University, to Dr. Pascal Serfontaine for his PhD on high fidelity Singer and 2-qubit gates for 2 electron spin qubits, and it has been very impressive. Well, a lot of you worked on error rates and to sort of say make qubits more controllable, more stable, to reduce the error rates. So that's impressive, and congratulations, and you are a really excellent winner of this award.
Yeah, thank you so much. So to be honest, I was sort of shooting for second place. That's what I was hoping for. Seeing sort of the field of competition, I wasn't even hoping for that. So yeah, I'm really, really grateful to receive this prize. And yeah, so let me thank you first of all for organizing this great award and this great award ceremony, and seeing also so many great pitches and such nice scientific works from various fields. But let me also say that, of course, especially in experimental physics, you never do it alone, right? So usually I have a big slide thanking all contributors, and there's a bunch of names. It didn't really have space for that today, but really there were so many people who contributed to that work on the theory side and also on the experimental side. And I want to thank all of you. I'm not gonna go through names now, but yeah, thank you. I think without big support also from my institute, this work could never have been done, right? You don't buy a fridge from your own money. So
thank you, Pascal. Thank you for that, and sincere congratulations. So the last thing we have to do during that award ceremony is to announce the audience award. First timer, to be honest, it's the first time that we give that award, and we were really, really wonderfully surprised by the huge amount of people who participated in that, and we have a clear winner. And let me look at the back of the studio. Do we have a slide to show? Can we? Yes, I see thumbs up. So drum roll. The winner of the Audience Award of the Quantum Future Award 2021 is Cem Gunnar from the Humboldt University in Berlin.
Yeah, thank you very much. I mean, I think a lot of my friends that were aware of this was watching me. I guess they did support me. So I'm happy to have been able to talk to an audience. And I'm happy that they liked it. So thank you very much.
Thank you. And thanks to the Ministry for the generous support in the preparation and in the execution of that award, and of the Quantum Future Academy that basically is attached to that award as well. Thanks to Ina Schiffer and her team. Thanks to Anja Karliczek, the Ministry of Research and Education in Germany. Thanks to our jury, to Oliver Benson and Alexander Regnat, and Christopher Gross, who prepared with us, and to all the people who did some preparation work. There is indeed, as Pascal already said, it's always a huge group of people involved in that. And what we have now here is just the result. Hopefully, in the next year, we will have a live event. We will not promise anything, but it would be good to see the qubits flying live. Thank you, everybody, for your contribution. And of course, we do hope to see you in the near future, but latest next year. Thank you very much.